All right, you guys, now we're going to begin to talk about the graph of the inverse function, okay? So it says, suppose that A and B is a point on the graph of a one-to-one function, f, defined by y equals f of x, the b equals f of a. This means that a equals the inverse function of b. So BA is a point on the graph of the inverse function, okay? So what that means in that complex definition is that if you have a point that is on your graph of your function, so for example here, AB, and you want to determine what coordinate is going to be on your inverse, because of the property between a function and its inverse that the domain and ranges are flip-flopped, the coordinate on the inverse would be BA, okay? Notice that the signs don't change on those coordinate values. The only thing that happens is that the placement of A and B, they change positions. So if A on the function was in the domain, it's the input, the x value, A is now in the range, or the y position on the inverse, okay? So the coordinates just change positions. That is all, okay? So let's look at this. So we have this theorem that says the graph of a one-to-one function f and the graph of its inverse function f to the negative 1 power are symmetric with respect to the line y equals x, okay? So if you're looking at this picture, the blue is the function, okay? So notice if you look at this first coordinate, a subscript 1, b subscript 1. Okay, if I want to find out where that matching point would be on the inverse, all I have to do is interchange the x and the y coordinates. So the point B1, A1 would be on the inverse. Okay, and you'll notice that for all of the points, all they did was change positions. Now, since they did that, anytime you have a function and its inverse function plotted on the same picture, they should always be symmetric with respect to the line y equals x, because in order to graph them, all you did was switch the y and the x coordinates. So they should always be mirrored images across this line, okay? So that's helpful because if they ever give you a picture of a function and an inverse together, and if you can't evenly split that graph between this line y equals x, then those two pictures that you've been given are not inverses. Okay, inverses will always be symmetric with respect to the line y equals x. Okay, so let's look at this example problem. So this problem says the graph in the figure, which I posted below, okay, is that of a one-to-one function y equals f of x. They want us to draw the graph of its inverse. Okay, so let's look at the coordinates really quickly. So if these are the coordinates on f of x, okay, then the coordinates on the inverse, all right, so if the point -2, -1 is on the function, then that means the point -1, -2 is on the inverse. If the point -1, 0 is on the function, then 0, -1 is on the inverse. And if the point 2, 1 is on the function, that means the point 1, 2 is on the inverse, okay? So if we plotted those points, so that would be -1, -2, then we would have 0, -1, and then we would have 1, 2, okay? And we drew those, okay? We'll see that our graph is symmetric with respect to the line y equals x, which it should be because they are inverses. So let me show you their picture because it's a little prettier than mine. All right, so as you can see, those graphs are symmetric with respect to the line y equals x, which they should be because they are inverses. So remember, if they ever have you plot them, all you need to do is change the positions between the x and the y coordinates and use that to plot your inverse. Or if they give you the inverse graph first, all you could do is flip the coordinates and it'll give you the original function. Okay, cool.